In this video, I will talk about compositional software design. The ideas presented in this video are my version of a compositional software design philosophy, so they might not be similar to what you have seen in other videos or read in other books. The core idea is to break down bigger components recursively into smaller reusable components designed to be composed together to form composite solutions. You do so guided by the SCIFI principles, which I will explain later in this video. Following these principles tend to lead to increased reusability, implementability, and testability. It also tends to lead to a smaller, simpler code base long term and somewhat faster development. That is my experience, at least. The ideas that I'm covering in this video are a distillation of more than 25 years of software development, and that means that this video is a bit long. However, there should be some new ideas in here for many developers, at least, even developers with longer experience. So it is my hope that it will still be worth your time to watch it regardless of your experience level. I started as a web developer in 1998 and switched to being a Java developer in 1999. I have pretty much grown up with these ideas here on the right, such as solid design patterns, dependency injection, inversion of control, etc. What I have learned over time, though, is that while these ideas are inspirational, this is not how I develop software in practice. And by that, I don't mean that I never use these ideas, but I don't start with these ideas. So what am I actually doing in practice instead? The basic software design process is as follows. We start with the requirements here. We apply some design thinking to those requirements, and out of that process here, we get a certain set of solutions. Sometimes we find those solutions to be so elegant or useful that we give them a name, like solid or design patterns or a dependency injection or whatever. The problem with that is that sometimes we fall so much in love with these solutions that we try to reapply them in different contexts here. We sometimes do that under the guise of best practices. So we call them best practices and say, yeah, we can just reuse these ideas as is without having to do any design thinking in this context here. The problem with that is that it often leads to over-engineering or mis-engineering, because these solutions that came from another process here may not really be 100% suitable for this scenario here. What I would suggest that we do instead is that we do not reuse the solutions, but that we simply repeat the process in the new context. So when we have requirements set B, we apply design thinking to that requirement set and get a new set of solutions that are appropriate for this situation. I call this appropriate practices. And that is exactly what I wanted to focus on. Instead of memorizing all these solutions that came out of previous design thinking processes, I want us to focus on learning design thinking itself so that we can design appropriate practices for each of the situations or each of the scenarios that we are designing software in. And that is exactly what I'm trying to do with compositional software design. I'm trying to distill a set of design thinking principles that we can use in different situations and arrive at different solutions that are appropriate for the current scenario that you are designing a solution for. Of course, I'm aware that ideas such as reusability, testability, and composition are not new ideas. I'm not the first person to think about these issues. What is new in my version of compositional software design is a more systematic approach to composability than I have seen elsewhere. With that disclaimer out of the way, grab your popcorn and let's dive into it. One of the most important questions in software design is, what are you designing for? In other words,
what are you trying to achieve with your design. In compositional software design, what we are designing for is composability. And what we're trying to achieve with composability is increased reusability. In addition, we can also get increased testability and simpler, smaller code. From these three achievements, we can get a higher quality of the product, of the code. And from that, we can get faster development time, and we can also get a lower development cost. My version of compositional software design is guided by the SCIFI principles, and the letters in the SCIFI acronym stand for split, connect, improve, facilitate, and iterate. And more specifically, that means split a unit responsibility recursively, connect the resulting units, improve interfaces of units, facilitate the use of units, and iterate on the design, because you won't get it right the first time. The stop condition for all of these principles here, all of these actions, is that you only do them when they are beneficial to you. So you only split a unit into 2 units if you actually have some kind of benefit from it. You only connect the resulting units in the most advanced way if you actually get a benefit from connecting them in that way. And you only improve the interfaces if you get a benefit, and you only facilitate the use of the units if you get a benefit, etc., etc. And you can do this both during the design phase or during coding, meaning you can use the SCIFI principles already during the design phase before you even start coding anything. But you can also do it, of course, during the coding session, but it's completely up to you. It's not something you have to do during programming or before programming. You can do a bit of this before you start coding and a bit of it after. That is usually how I do it. Let's dive into each of these principles in more detail. When we split a unit, we split it because we want to achieve some benefit from that split. When we split a unit's responsibility recursively, we typically split big responsibilities into smaller and smaller responsibilities until at some point we no longer gain any benefits from splitting the unit any further. The splitting typically stops when a unit's responsibility is small enough to implement and or test in isolation, or there are no more parts of the responsibility that you want to reuse or replace in that unit. So, how do we split responsibility? How do we split a unit A into a unit B and C? In other words, if we have a unit A, how do we identify a B and a C inside of A? Meaning, how do we identify responsibility to reuse or identify responsibility to replace? When we split a unit for reusability, we do so by identifying some responsibility within that unit that can be reused in another context. For instance, here we are splitting A into B and C can be reused in another context, which here is denoted by D. And that means that you can reuse C independently of B. So even though A consists of B, which uses C, you can reuse C in another context, D, here as well. Splitting a unit for replaceability is a little bit different. You're still splitting A into B and C, but instead of focusing on the reusability of C, we are focusing on the replaceability of C. So we want B to be able to replace C with something else. In other words, we want to be able to reuse B independently of C, not C independently of B. It is the replaceability of C that leads to the reusability of B. When we split a unit for replaceability, we achieve what I refer to as two-way reusability. And two-way reusability means that both of the units that results from the split can be reused. So we can reuse B independently of C because we can replace C with E. But we can also reuse C independently of B, for instance from another component D. By designing for replaceability of C, you get reusability of both B and C. You design for replaceability via the connections between your units, as we shall see later. By the way, if you are using a programming language such as Java or C# that has the concept of interfaces, you might be wondering when to use an interface and when not. My personal rule of thumb is this. If I am designing for replaceability, for two-way reusability in other words, I use an interface. In the example on the left, B references an interface which C and E implements. B can thus be reused with any implementation of that interface. If, however, I am only designing for one-way reusability, I tend not to use an interface. In the example on the right, B does not need to be able to replace C, so B can just reference C directly. C can still be reused from D, even if C does not implement any interface. There are many ways to split a unit's responsibility, and by a unit, by the way, I mean either a class or a method or a function. But there are three classical responsibility splits that you should probably know about. The first is the splitting of action from action. The second is the splitting of action from scope or context. And the third is the splitting of action from state. The first type of responsibility split is the splitting of action from action. Now, if you imagine that you have a single method or function or class which has two responsibilities embedded inside of it. First, it loads a file and then it calculates a hash value from that file. You can split that either into two methods. If this was one method, you could split it into two methods, or one function, you could split it into two functions. One function that or method that loads the file, and another one which calculates the hash. If this was one class, you could also split it into two classes, and then it would of course naturally be split into two methods as well. One class that is responsible for loading the file, and another class that is responsible for calculating the hash. The second classical responsibility split is the splitting of action from the context or scope within which the action is taking place. If you imagine you have a unit that performs the following 5 steps here: opening a database connection, begins a transaction, perform database actions, commit or roll back the transaction, and close the database connection, then this action in here can be reused independently of the context, the connection, and the transaction in which it is taking place. We do that simply by splitting the unit into two units, where you take the action here, or the actions, out of the first unit here. This, by the way, is what the template method design pattern is designed to do. You can split this even further, so you can split the context here into two contexts. One context of an open database connection, so you open and close it, and another context here, or scope, if you prefer that word, of beginning a transaction and committing or rolling back that transaction. And then you have the action here, which can now be reused independently of transactions and database connections. The third classical way to split responsibility of units is the splitting of action from state. And by action and state, I actually mean actions that use state and actions that manage state. If you look at this tree node implementation here, then you can see it has a set of methods here: add child, remove child, get children, etc., which are all managing the state, the internal state of the tree node. Then it also has two methods down here, count nodes and count nodes matching, which are not actually setting or changing anything internally in the tree node. So it does not actually update the state or manipulate the state of the tree node. They only use the internal state of the tree node. So these are actions that are using the state, and these up here are actions that are somehow managing the state or giving you access to the internal state, such as get parent. It doesn't change anything, but it gives you access to the parent tree node of this tree node. You can split this unit in two like this. We keep all the state managing actions in one class or in one unit here on the left, and then we move the two actions that work on the internal state of the tree node to its own class here. So we have a count nodes and a count nodes matching method, which have been moved to a tree node util class. This way, if you imagine, for instance, the tree node was an interface, for instance, a Java interface or an interface in C# or something like that, then if a new class has to implement the tree node interface, it only has to implement these state managing methods here. It does not have to implement the count nodes and count nodes matching, because these methods can be reused as is. Because as long as the new implementation of the tree node interface implements these methods, then these methods over here can perform their operations. They can perform their responsibility. And so that what we have done here is exactly to separate the actions that manage state from the actions that only use the state. After splitting our units, we need to connect our units again so they can be used together in a composition. The way we connect our units determine what level of composability and thus reusability and replaceability that we can achieve. When deciding how to connect your units, there are two important aspects of connecting your units that you need to take into consideration. The first is connection direction, meaning the direction of the connections between your units. And the second is connection mutability, meaning the ability to change the connections at runtime. Let's first talk about connection directions. Imagine that you have a caller class which calls another class here which loads a file and calculates a hash. Imagine then that we split this class up here into two classes where one of them is loading the file and the other one is calculating the hash from that file. In how many ways can we connect these resulting three units? One way to connect these three resulting classes would be to have the caller call the load file class and have the load file class then call the calculate hash class. Another way to connect the three units would be to have the caller class here called the calculate hash class, which then is given a source from where to read the file that it's supposed to calculate the hash from, which is the load file class here. And then the calculate hash class will load the file and calculate the hash and return the value to the caller. A third way to connect these three units would be to have the caller first call the load file class and then call the calculate file class afterwards with the bytes loaded by the load file class. This way, the load file class and the calculate hash class don't need to know anything about each other. Only the caller needs to know about both of them. There are probably more ways to connect classes than the three here that I mentioned here. You could, for instance, create a third class that coordinates between the load file and calculate hash class so that the caller doesn't have to know anything about these two components here, or these two classes. But what is important is not to cover all the many different ways in which you can connect your units. What matters is that you think about that there is a difference between whether you use this model here or this model here, this direction of the connections here, or this direction of the connections here, or this model here, or some other model. You need to think about it because it affects how you can compose your classes later on. As a rule of thumb, the fewer other units a unit needs to know in order to do its job, the more reusable that unit tends to be. As we have just seen, the direction of the connections between your units has a direct impact on how many other units each individual unit needs to know to do its job. Thus, the direction of the connections between your units has a direct impact on their reusability. The second important aspect of connecting your units is the issue of connection mutability. Connection mutability can be classified into two different categories, or two overall categories: static connections and dynamic connections. Static connections are not changeable at runtime, meaning they are not mutable at runtime. For instance, a hard-coded local reference to a class inside of a function or method, or a hard-coded member reference to a given class, cannot be changed at runtime. It is defined at compile time, and that's how it stays during the entire runtime of the application or the system. Connections that have a dynamic mutability, though, can be changed at runtime. There are three major types of dynamic mutability of connections between classes or units. The first is creation time mutability, and that basically means that you can set the connection from one class to another class at the time you create the first class. You typically do that by injecting a reference to the second class into the constructor of the first class. We know this from dependency injection. The second dynamic mutable connection method that you can use is configuration time mutability. And that basically means that you can change the connection from one class to another class at some point after that object has been created and before you use it. You typically do change or mutate the connection from one class to another by injecting a reference to the second class into the setter method on the first class. This is also sometimes called setter injection. We also know this from dependency injection. The last category here is call time mutability. And basically that means that every time you call a given method or function, you get to specify at call time what other class it should be using to do its job. So you typically provide a reference to that other class as a parameter to the method that you are calling, or to the method or function that you are calling. This is what I call parameter injected references. Let's have a look at a couple of connection mutabilities as examples. The first one here is what I call static member connection. And it's static not because of this part, the declaration part here, but because of the instantiation of a new C right here at the declaration of this C1 variable. You cannot change later in the lifetime of B, you cannot change what C that this object here is referring to. It will always refer to this C here that is instantiated here. Also, you cannot instantiate a subclass or anything else than that. It is just completely static. Once this C is instantiated, then this B instance here always refers to this C instance here. Of course, you could add methods that could make this more mutable, but in this example, as you can see, there are no more methods, there are no more ways to change this C1 variable or member variable here. So that is what I call a static member connection. And it means a hard-coded reference from B to C. The second example of connection mutability is what I call creation time mutability. And basically what it means is that you can inject a reference to the class or the object that you want to reference in the constructor of the object that you're creating. So in this example here, we are creating an instance of B, and into the constructor of B, we can inject an instance of C. This gives us the possibility to specify at the time of the creation of B exactly which instance of C that we want to inject. For instance, we could have one C object that we are sharing among many B instances, or we could give each B instance its own C instance, or we could even use a subclass of C, because after all, that is what inheritance gives us. However, after creation of B, as you can see, there is no code anywhere that allows any further mutability of this variable here. So we can specify which C to reference to connect B to at creation time of B, but not after that. The third kind of connection mutability that I will show here is what I call configuration time mutability. And as you can see here in class B, we have a setter here called setC1. This setter allows us to set a new instance of C on this B instance at any time in the use time of, or in the lifetime of B, in which we want to call this method. And as you can see, it sets here C1, this reference here, to the new C. We also have creation time mutability here, so we can specify both C at creation time, but also later at configuration time. And the reason I call it configuration time is that it is after creation time, but it is before the time that we are actually using B. Now you might wonder, what would we use B for? Because there are not really any methods here that can do anything. But just imagine there were some methods here that can actually do something later on. But they're not shown here. So anyways, configuration time means after creation time, but before you actually use the object. The fourth example here of connection mutability is what I call a static local connection. You can see that this method here do inside of class B is creating a new instance of C. And it is not possible to change what instance of C is used, nor if you want to use a subclass of C or anything like that. This reference here, this connection between class B and class C is completely static, it's completely hard-coded, and it's completely immutable in the code. The fifth type of connection mutability is what I call call time mutability, which is basically a parameter injected reference, which basically just means that you are passing a parameter as a parameter, a reference to the object that you want B to use. As you can see here, the do method here takes a C instance as parameter. And then inside of the do method here, B can do whatever it wants with C. This means that you can change what instance of C that you're using for every single time that you are calling the do method here. If you need to use a separate C for every time that you are calling do, then this is a smart way of doing it. Otherwise, maybe think about whether a setter injected reference or maybe a constructor injected reference would be smarter instead. By the way, the principles of connections and connection mutability do not only apply to classes and objects. They can also be used in functional programming, in function composition. And in this example here, I'm showing you an example of creation time mutability when composing a new function, actually a new lambda expression. But as you can see, we have a function here called compose, and compose is taking one function here, f1, and another function here, f2, as parameters. And what it is returning is, as you can see, the return type here is a new function that takes a string as input and returns a string as output that combines f1 and f2. So what it does, it takes a string here, p1, and then it returns f1 applied to this string, plus, which means concatenated with, because we're working on strings here, f2 applied to this input string here. So basically, at the time that we are creating this lambda expression, this new function here, we can set which function f1 and f2 that we want the returned function here to use internally. But once this function has been composed and returned, you can no longer change f1 and f2 anymore. So you only have creation time mutability, meaning you can only set the references to point to something when you create the function. Let's sum up what we have talked about with regards to connection mutability so far. Static, hard-coded, and immutable connections are bad for composability. Your composition becomes static. It becomes inflexible. It cannot change at runtime. Dynamic, mutable connections are better for composability because you can compose more freely at runtime, and you can even recompose in some situations how your classes and objects are connected at runtime. When we look at dynamic or mutable connections, there are the three categories here: creation time mutability, configuration time mutability, and call time mutability that we have already talked a little bit about here. And creation time mutability is good if you don't need the connection to change during the lifetime of the object, but only you can assess whether that is the case or not. Configuration time mutability is good if you need to sometimes change the connection of an object, but not every time you use it. And call time mutability is good if you need to change the connection of an object almost every time you use it, meaning every time you call the methods that use that connection. And here I've called them connections, but in other literature you will see them referenced as references, or called references, or dependencies, right? So this could also be called creation time dependency injection, configuration time dependency injection, and call time dependency injection. And whether you want to call it that or connections, or that is up to you. I don't have any hard opinions about that. The first I in SCIFI stands for improve interfaces. The idea is that we want to improve the interfaces of our classes, interfaces, and methods and functions in order to make them more reusable. If you look at this example here, we have a class called hash calculator, and it has a method called calculate hash. As you can see, this method takes a byte array as a parameter. Basically, that means that if you want to calculate a hash value from all the bytes in this byte array here, you can use this method. However, what if you wanted to calculate a hash value from only part of this array here, or part of an array? How would you do that? Well, right now, the way this method here is structured, you would unfortunately have to create a new array, copy the section of your original byte array into that array, and pass that array to this method here. What we could do instead is we could change the interface of calculate hash so that instead of just taking a byte array, we could take a byte array, an offset from where to start calculating the hash value, and a length, which is how many bytes from this offset we should include in calculating the hash value. Now we can calculate both the hash value from a full byte array by simply passing in 0 here as offset and the length of the array as length. But we can also calculate the hash value of a slice of an array, a subpart of an array. And this makes this method here more reusable as it already is. Or it's at least easier to reuse than this version of the method is. Obviously, it's a little bit annoying if you actually want to calculate a hash value from the entire number of bytes in an array to have to pass in 0 and then source.length as parameter here, or the array.length as parameter here. So we can improve the interface a little bit more by overloading with a method version here that takes only the byte array and calculates a hash value from the entire byte array. And we can have this method here, this version here, when we want to calculate the hash value of a part of the array. The F in SCIFI stands for facilitate the use of the core units. If you imagine that you have a system where you have these 6 core units here, and that these units need to be composed together into this graph of objects here in order to solve some problem or perform some functionality, then it can be quite cumbersome and tedious to have to learn how to assemble all of these components together yourself as the one who is writing code that uses A and then B, C, D, E, and F inside of A or from A. What you can do in order to make it easier to use this object graph here, or to easier to use it but also to compose it, is you can add some extra units which are only added in order to make these components here easier to use. For instance, you could use the builder pattern and add a builder and have this builder build this entire object graph for the user of A. And I'm not talking about the end user, I'm talking about the programmer who wants to use this object graph. Alternatively, you could add a facade class in front of this object structure here. And so the user of the facade would not need to know how to assemble this entire graph here. The facade would do it for the user behind the scenes. Or you could use a dependency injection container which can wire up all of these classes together. So you simply ask the container for an instance of A, and then the container knows how to wire it up with the B, C, D, F, and E. And there are probably other ways of facilitating the use of the core units than these 3 methods here. There are other design patterns, and you can probably come up with your own solutions. The idea is basically, or is just, that you are adding some components to your system whose only purpose is to make the core components of your system easier to use. So these components here are not components with business functionality. They only play a support role in your system. In other words, these classes are only helper classes in your system, and they help make the core classes easier to use. The last I in SCIFI stands for iterate on the design, because you probably will not get the design right the first time. Design refinement is a recursive process, and the stop condition for this recursive process is the only if beneficial principle, meaning you only keep refining the design if you can see that you can get some kind of benefit out of refining the design. You stop refining the design when further design refinement is no longer directly beneficial. Once you start designing for speculative benefits, meaning benefits that you might get in the future but you don't know for sure that you're going to get in the future, it is time to stop refining the design. Here is an example, or just an illustration, of what this recursive process of iterating on the design looks. So you might start with a big component here in iteration 1, because that's all you need. You may not at this point need to split the units any further than this. In the second iteration here, something happened. Maybe some new requirement in a new user story came up, and you now see that it is useful to split the design here, or split this class into 2 units. Then in the third iteration, something new happens where you judge that it makes sense to split this unit into 2 smaller units while keeping this one the same size. And in the fourth iteration, maybe you realize it makes sense to also split this unit into 2 smaller units. This is just an example. We could have stopped in iteration 3 or in iteration 2 or already in iteration 1 if that is what made sense for the current project. This is just an illustration of how that you might iterate on the design over time. You're not necessarily doing all of this upfront. This may happen in the beginning of the project. This may happen after 3 months. This may happen after 6 months. This may happen after 1.5 years. Who knows, right? That's not what matters. What matters is you refine the design when you benefit from refining the design. So you redesign when you benefit from the redesign. Let me sum up what I have been talking about in this video about compositional software design. Compositional software design is about designing for composability. And we design for composability because increased composability brings increased reusability. My version of compositional software design is guided by the SCIFI principles. And the SCIFI principle stands for split unit responsibility recursively, connect the resulting units, improve the interfaces of these units, facilitate the use of these units, and iterate on the design, which basically means iterate through this process. We only iterate through the design, we only redesign or refine the design as long as it is beneficial to us. We do not refine the design for benefits that are speculative, meaning things we think we might need in the future. We only do it if we actually know we're going to need it either now or in the near future. These 5 principles here can be applied either during the design phase or during coding. So either before you start coding or while you're coding. In a bit more detail, when we split responsibility, we do that because there's part of the responsibility of the original unit that we want to reuse or that we want to be able to replace. A couple of common ways to split responsibility is to split action responsibility from action responsibility, or action from scope or context, or action from state management. Once the units have been split, we need to connect them again. And the way when we connect them, we need to think about the direction of the connections between the units, and we need to think about the mutability of these connections. Third, we improve the interfaces, and we do that in order to make the interfaces more versatile so they can be used in more scenarios. When an interface or when a component can be used in more scenarios, it is more reusable, and thus we can reuse it more, right? When we have done that, we facilitate the use of the core units, and we typically do that by adding support units that make it easier to use the core units, such as a facade or a builder, or maybe we use a dependency injection container or something like that. And finally, we iterate through these four principles here, or these four activities, as long as it is beneficial for us to do so. Now let's have a look at a case to see how to apply these SCIFI principles and the other details that I have described earlier in practice. The case will be calculating a hash value from a file. I have hinted at this case a couple of times during this video already. And there will be 4 iterations of requirements plus subsequent design changes afterwards according to the SCIFI principles. In the first iteration of this case, the requirements are simply to calculate a hash value from a file, and the hash algorithm is A or 1 or whatever. It's not really important. By the way, when I show you the code, which I will soon, please keep in mind that the hash algorithms that I'm showing are really, really terrible hash algorithm implementations. You should never use them as I have implemented them in this case. But that is not really what is important here. The important thing is not how the hash algorithm is implemented. It's how we structure the code. Okay, that's also why I write the hash algorithm is not important. In the first iteration of this case, we can implement the requirements using a single class here, the file hash calculator class here. It has a single method here called calculate, which returns the hash value, the hash code, as a byte array. And what it does is it takes the file path that is passed as parameter, opens a file input stream using that file path, and then it reads all the bytes here. Then it simply iterates through all the bytes and sums them up and uses that as the hash value. Like I said, this is a very bad hash code, so don't use it in reality, but it doesn't really matter for the sake of this case. Then what it does finally here is it takes the hash here and turns it into a 4-byte array and returns that. And in the main class here, it only exists to show you how to use the file hash calculator. And you would simply create a new file hash calculator like this, called calculate, with a path to the file you want to calculate the hash value from, and then you can iterate through the hash value and print out each of the bytes in the hash value. And that's pretty much it. And for, like I said, for the first iteration of this file, or this case, first iteration of this case, implementing the requirements in one class is perfectly fine. There is no benefit, there's no big benefit in beginning to split this up. After the first iteration, the design looks like this. We have a single class called file hash calculator, and it both loads the file and calculates the hash code within the same class and the same method. So there isn't really much of a design at this point. It's just one big class, which isn't even that big, as you have seen. In the second iteration, we have a change to the requirements. We have to add a hash algorithm, and I've called it B, as an option. So now we have both algorithm A and algorithm B as options. Now again, the concrete implementation is unimportant because it's not about hashing this case here. This case study is about design. In the second iteration, the file hash calculator from iteration 1 has been split into a file loader and has algorithm A, and then I have added hash algorithm B, which was the new requirement in iteration 2. I've also split this into bytes out, the part of the hash algorithm that converts the integer hash value
into bytes, into its own class. If we look at the main method here, you can see we now have a file loader being created, and then has algorithm A being created here, and then the file loader is being asked to load the file, and then the hash algorithm is calculating the hash value from the data stored in the file, and then the result of the hash value is simply printed out here. If we look at the file loader, it really only contains very little code. You can see here has a load method, takes a string as a parameter, the file path as a parameter, and then it simply opens a file input stream and returns everything that is returned from the read all bytes method of the file input stream. The hash algorithm A is the hash algorithm that we already know. So it still returns the hash value as a byte array, has a calculate method here, takes the bytes, the input data to calculate the hash value from here as parameter, and then it simply creates the sum. Now it's called sum, we should probably call it hash instead, hash value, like that, and yeah, that's really what it does. Then it calls into bytes and return this int into 4 bytes, a byte array of 4 bytes, which is then returned here. The reason I split this part into its own class is because in hash algorithm B, we also need that functionality. So there's no reason to replicate it, right? We need it both from algorithm A and B. So it has been separated into its own class and can then be reused both from A and B. Yeah, in hash algorithm B, we've made a small change to the way the sum is calculated, and again, we probably should call it hash value instead of sum. So what we're doing here is, instead of simply summing up all of the bytes, we are multiplying. We are multiplying each of the bytes in the input byte array with its position in the byte array plus 1. And the reason we add 1 here is so that when I is 0 for the first byte, that I being 0 does not cancel out the value of the first byte in the hash value. So we add 1, so it will multiply from 1 and up to this value. So obviously if this value here is 0, then yeah, it will be cancelled out, but so it is. And then again, once this hash value has been calculated, it is converted into bytes, 4 bytes in a byte array and returned here. The int to bytes class is simply these 6 instructions here. Create the byte array and then write to each of the bytes in the byte array and return it. So that's about it. So as you can see, there's one little change in the requirements that we now needed to add one hash algorithm B to the system. Induced me to split this file hash calculator into a file loader, hash algorithm A, and a hash algorithm B, and into bytes classes, right? We don't need to do anything more at this point. This is enough at this point. After iteration 2, we have the following components. We have the component that loads the file loader. We have the hash algorithm A, and we have the hash algorithm B or class, and then we have the class that converts integers to bytes. In iteration 3, the requirements are updated as follows. First of all, we have to add HTTP as a file source, meaning we have to be able to download a file over the internet and calculate a hash from that. And both hash algorithm A and B must be applicable to both local files and files downloaded via HTTP. Code-wise, the only thing that has changed from iteration 2 to iteration 3 is the addition of the HTTP loader class, which you can see on the screen here. It has a single load method. It takes a URL string as parameter, creates a URL object from that URL string, opens a URL connection, and then gets the input stream from it and reads all the bytes from the input stream and returns them as a byte array. So this is very similar to what is going on in the file loader, except this is using HTTP to access the file instead. In the main class here, you can see an example of how to use the HTTP loader. Here you can see it's very similar to using the file loader. You can see here is a load, that is the call to the load method, which will load the front page of my website here, and then it's going to take the data returned here and put them into the hash algorithm. And we could have used hash algorithm B as well. It would have been no big difference. As you can see, they are designed to have the same interface, even though they do not implement the same Java interface. They have the same method signature so far. So that's what I meant by having the same interface. After iteration 3, we have the following classes. We have the class that loads the file. We have the class that can download a file. We have the hash algorithm A, and we have the hash algorithm B, and we have the class that can convert an int into bytes. The fourth iteration is a redesign iteration, aka a refactoring iteration. And it's an iteration that I, as a developer, has decided to introduce in the project to make the core hashing classes easier to work with for me as a developer. So if this was a real project, I would go to my management and push back against just, jumping on the next ticket or the next story and say, I need to clean up this code a little bit because it's gotten a little bit messy and hard to use. So before I take the next ticket, I need to do some cleanup. And what I will be doing here is to add a facade that groups the needed components together. The one class that loads data and another class that calculates a hash code on the data. And then I will add a facade builder that makes it easier to compose the facade. So you don't have to manage all these different classes and you don't need to know about them, as you will see. Code-wise, the difference between iteration 3 and iteration 4 is that I have added a data source interface, a hash algorithm interface, a hash builder class, and a hash facade class, and made some changes to the main method here that shows how to use these classes. To understand the design changes that have been made, let's start by looking at the hash facade class. The hash facade class has a reference to a data source, and remember, data source is an interface. It has a string to the path that the data source is going to use to load the data, and then it has a reference to a hash algorithm, which again, remember, is an interface that I created here. The hash facade class has a single constructor here, which takes a data source path, and a hash algorithm as parameters. And these are stored internally. Note that you could have designed these data sources differently, so that instead of the data source path going into this hash facade constructor, they could have been injected into the constructors of the file loader and the HTTP loader instead. And if they were, then this data source class here, we would only need this data source parameter here. We would not need this because it would already be stored internally in the HTTP loader or the file loader. However, then those
classes, those objects, once you had created an instance of the file loader, it could only load that one single file, because you would have stored the path to the file to load internally in the object, instead of passing it as a parameter to its load method. So you can debate whether one design or the other is better or not. But this is a choice, right? As a designer, you make a lot of choices, and some of them are possible to design in different ways with different kinds of trade-offs, pros and cons. Anyway, so this is what it does. It stores these references here to the data source path, and the hash algorithm internally. And then it has a calculate method, which simply calls the data source and calls the load with the data source path as parameter. And then it calls the hash algorithm calculate with the data returned by the data source. And then it returns the hash from that. And that's what the facade does. It's very small, as you can see in code, right? And the builder here helps us build the facade. I can show you, but it's not super interesting. It has a couple of methods here. It says from file, from URL, that signals where to load the data from. You can see it takes a string as the path, either file path or URL path. And then you can call these calc hash and A and calc hash B, which signals internally to the builder which hash algorithm to use. And then there's a build method that basically takes creates a data source and a hash algorithm depending on whether you specified a file path or a URL path by calling these methods that I showed you above. And then at the end, and also here you can see it creates a hash algorithm depending on whether you called calc hash A or calc hash B. And then it returns a new hash facade with the data source path, and the hash algorithm. And when we look at the main class here again, you can see that we can access the builder here through this static builder method. If we look at the builder, you can see that it is up here, returns just a new hash builder, a new instance of this class. And on that instance, we can call calc hash A, and we can call from file or from URL, and then we can call build. That gives us the facade. And that is the facade that we can now use to calculate the hash. The builder makes the hash algorithm classes and the data source classes easier to use. First of all, by making the code a little bit more readable. Here, it is quite clear that I am asking the builder here to use hash algorithm A on this file here, data/data.txt, right? If you read it, it kind of almost reads like natural language. Calculate hash algorithm A from this file, and then you call build to build the facade, right? So that is one way. It makes the code a little bit more readable. And second, once I have the builder, if I use code completion, I pressed Control Space here, you can see what methods are available here. And I can see that both calc hash A and hash B are available. And if I now just want to see what methods are available for calculation, like which hash algorithms are available, I can simply just move the cursor here a few characters in, and I can see only hash A and hash B are available. I could change it from A to B simply by doing like this. And similarly, if I wanted to see what methods were available for loading data, I could go down here to this line and simply move the cursor a few lines in, and you can see, I can see here that there's a from file and a from URL method available, so that it is very easy for me to see what data sources are available to me here. There's one that can download from a URL and one that can read from a file. Okay, so The builder here also makes it easier to learn what options you have with the classes in your system, because when you design the builder actually to take advantage of code completion, obviously if I had called these methods here with the hash algorithm A and B, if they had been called like very different things, then I could still see them, but it would maybe not be as easy, right? Like if the fact that all the hash methods here, all the algorithm methods, they start with calc, makes it a little bit easier. But if they had completely different names, I could still find them from the builder. But as you can see, there are more choices now here to navigate. But they would still be available here, right? But I also get all this noise down here, which I don't really need. That's why when designing a builder or any other class, I sometimes like to design them for easy use with code completion, so that you can see as soon as I just step a couple of characters in, I get my choices reduced to that which kind of are in the same category of methods. Same here, right, with from URL here. But anyways, so using the builder makes the code easier to read. It also makes it easier to find out what options you have in your system. And you don't have to remember all the class names and how to configure them and all that stuff internally, because the builder kind of remembers that for you. All you need to know is how to create the builder, and from the builder you can figure out the rest through the use of code completion and simply by exploring the builder's API. After the fourth iteration, the code base consists of the following components. There's still the original ones, the load file, the download file, the calculate hashcode A and calculate hashcode B, and the int to bytes class. And then what was added in the fourth iteration was the data source interface, the hash algorithm interface, and the facade, which has a reference to a data source and a hash algorithm and a data source path internally. And then the builder class, which can help us build a facade and specify which data source path, and which hash algorithm to use in the facade after it has been constructed. Just to be absolutely sure that I mention it and sure that you are aware of it, designing for composability is not the only thing you design for in an application. Imagine here, in this case here, we have a big application here, and most of it has been designed for composability. We are designing for reuse. Out here, reuse is the most important design factor, beyond, of course, the functionality of the system itself. But maybe we have a corner here in which the most important design factor is performance. And sometimes when designing for performance, we have to deviate from the composability principles described in this video. And for instance, you might have to merge a couple of components that you would have normally split up for reusability. You might have to merge a couple of them to avoid to have too many calls between these components at runtime. And there can be other examples too. Just remember that it is quite okay to deviate from designing for composability if you have something else you need to design for in a specific part of your application that is more important than composability. In the beginning of this video, I said that compositional software design can lead to a smaller code base in the long run. And you might be wondering how that is possible, because after all, if we are splitting the code base into a lot of small pieces, will we not end up with a larger code base than we would if we did not split it up into as many small pieces? And the secret is that what happens is not actually like this. What happens is that you break down the code into smaller pieces in the beginning of the development, And during this phase, yes, you do get more classes and more small pieces of code than you do in the beginning if you don't break it down as much. However, over time, because you can reuse so much of the first code that you write, the new code that you add to the project will be smaller, will tend to be smaller, and thus in the long run, new additions to the code base will be smaller than if you do not focus as much on reuse. You can see here the two phases here of the development of the code base is what I call the decompositional expansion and the compositional contraction. And during the decompositional expansion, you will see a larger code base than if you had not focused so much on reusability. So at first, it seems like you are focusing a lot on reusability, but instead of having less code, you get more code, and this might feel a little bit weird. However, as your project grows, you will at some point get into the compositional contraction phase, and that is when you start to have more and more benefit of all the classes that you made early in the or functions, classes or functions that you made early in the project, and now your code base evolves with less new code being added as you add new functionality. So it grows slower once you get into the compositional contraction phase. In the beginning of this video, I also mentioned that I believe compositional software design can lead to increased development speed, so faster development speed. And you might be wondering how that is possible. Let me explain here. A typical application will consist of layers that are more focused on the business, and then you will have some mediating layers, and then at the bottom you will have some layers that are more focused on technical aspects of your application, such as connecting to a database and reading from a file system or sending messages over a network, calling APIs with HTTP, etc., etc. In the beginning of your project, when you add a new business component, you will also have to add some of these mediating layers and the technical layers to your application as well. However, as your project progresses and you need to add new business components to your system, you will be able to reuse more and more of the technical layers here. So you will be working more and more of your time up here in the higher layers. Once you get to that point, you will not be adding as much new code to the system, and you will thus be developing faster. This actually ties back into what I was talking about before. In the beginning of your project, you're in the decompositional expansion phase, and you're adding more code to the project than you would if you did not focus so much on composition or composability. During that phase, development speed is also lower than it could have been if you had not focused so much on reusability. However, as you move from the decompositional expansion phase into the compositional contraction phase, you start adding less code than you would have if you had not focused so much on reusability. And as a result of that, development speed tends to start to increase. And at some point, you will get to a faster development speed than if you did not focus so much on reuse. So that is why I believe compositional software design leads to both a smaller code base and also faster development over time. In this video, I have mostly focused on how to use compositional design techniques in object-oriented programming. However, you can also use compositional design techniques outside of object-oriented programming. For instance, it is quite normal in functional programming to compose one function from other functions. So there you can use compositional techniques for function composition. You can also use compositional design techniques at the architecture level, and by architecture level I mean at the process level, at multiple processes. For instance, the Linux command line tools are often, many of them, designed to be composed together so that the output of one command line tool can be used as input for another. And finally, you can also use compositional design techniques at the data level, so that you can design your software so that you can compose different data together to form a larger whole. For instance, you could design a chart component to be able to show data from different data sources, and so it would be up to the user to compose a chart from whatever data they wanted to display in that chart. There is a lot more that could be said about compositional software design, but I have to stop this video somewhere, and this video is a decent introduction as it is now. I will probably return to this subject in future videos. Remember to check out the description below this video for references to similar videos or related tutorials. And if you like this video, please hit the like button, and if you want to watch more videos like this, please subscribe to my channel.